Okay, so again, now we're going to go through an introduction to the Crystal Violet Pivot Lab. All right, so when you open this reaction, when you open up this lab, it's going to ask us to measure progress in a different way. So in the last lab, we collected a volume of a gas. In this lab, we're going to look at the transmission of light, similar to what we've done with SPEC 20s and doing a Beer's law plot eventually. Okay, so it does start out in a somewhat confusing way. It describes the reaction that we're going to do and the color that we're going to be looking at. And then it shows sort of a weird music video, which I didn't find very helpful at all. So you can watch that, it's short. But what I want to show you is how to use the tools in this lab to collect data. Because if you can't do that, we can't answer any of the questions in it. So the first thing that we're going to do is we're going to look at the crystal violet solution with each color of LED light. And we want to see which one is best absorbed, all right, so that we can take measurements. This is kind of like when we did a SPEC 20 lab and we wanted to find the wavelength of maximum absorption. That's what we're doing here. So as you watch this video, right, you can move this cuvette, which contains the purple solution, okay, in front of each of the lights. So there it is in front of blue. Okay, so that's happening right here, okay, in front of teal, in front of green. And look what happens when we put it in front of the yellow. So there's the yellow. All right, and then when we try to pass the yellow light through the purple solution, some of it is absorbed. Okay, and then you keep going and you get to check all the other colors. All right, and you can see from this that that the yellow light is absorbed the best. So that's the first conclusion you're supposed to draw. Okay, which LED has the largest change in brightness or absorbance? All right, and I think we picked yellow for that. Okay. All right, now the next part is to use Beer's-Lambert law to determine absorbance and concentration as a function of concentration. And so you have to do some calculations with that down here in the table. But the first thing you have to do is measure the transmittance. And that is a little bit of a challenge to figure out. So I want to show you how to do that with the tools. Okay. So right now we have 0% crystal violet. And so we want to see how it absorbs the yellow light. Okay, so right now the light is passing through the cuvette at 0% crystal violet. You open up the tools and it gives you a bunch of these transmittance, I think, transmittance measuring tools, okay? So don't you agree that probably close to 100% of this light is being transmitted, right? The yellow didn't change very much. So I'm gonna pick the 80 to 100% range. You drag this little ruler down here below the yellow. All right, and we're looking at this circle here and we're trying to match it to the background color. Okay, so as I have it down here, do you see how the circle is whiter than the 81% background? But as I slide this to greater transmittance, right, there's like 94% transmittance. You can't detect the circle from the background. So you're going to pick some number where that's true, where your circle matches your background. I'm going to pick 97%. Okay, and then I go down to the table and I say 97% transmittance. Okay, Now, if we change our crystal violet to a 50% solution, I'm going to do the same set of steps. First of all, I'm going to get rid of this old ruler thing out of the way, okay, so I can see what's going on. I'm going to slide this yellow over again in front of the cuvette. So wait, I'm going to go right here, okay, and then watch it move behind the cuvette. See how it changed from yellow to orange? So right now the cuvette is in front of what was the yellow LED light, and some of the yellow light was absorbed. This circle down here is going to allow me to measure. This is a grayscale kind of thing, which is going to allow us to measure how much light was absorbed. So let's say maybe we'll try this middle range, 60 to 80%. So I'm going to take this down here. So I'm putting on 68%. The circle in the middle does not match the background. The circle in the middle is darker than the background. So that means I absorbed more light, and I'm going to slide it this way. Okay. Even at this end here, okay, 60%, and you'll have to be able to see this on your own computer screen. This circle looks a little bit darker than the 60 that I see here. So I'm going to go down to 60 to 40 to 60%. I'm going to measure with that one. Get rid of this. All right, and then you just play with it. Now at 51%, the inner circle is lighter than the background. So I'm going to say, all right, maybe a little bit more light was getting in. And now I'm getting into a closer match. I'm going to say at 50% crystal violet, I have 57% transmittance. Okay, and you're going to fill in this table. As you can see, you're going to go from 0 to 50% filling in this table. All right. Then over here for absorbance, we have to calculate absorbance from transmittance. And so it shows you here how to do that. Okay, negative log of percent transmittance over 100. This is just like the Beers Law lab we did. So let's see if we can put a formula in there. So negative log percent transmittance divided by 100. Okay, so you're typing in your formula like it's a spreadsheet. And then it gives you these values. Okay, so the higher the concentration of the crystal violet, the greater the absorbance. All right, so once all your data is filled in and your calculation is done, it says, what are we graphing here? Oh, we want to do absorbance versus concentration. Okay, so you're going to decide which axis we have. What do you have for your y-axis? I'm going to select absorbance. And for my x-axis, I'm going to choose concentration. All right, so I only had 2 data points, but of course you're going to have 6 data points here, I think. Describe your results. What's the shape of the graph? What does this tell you about the crystal violet solution? Predict the absorbance for 45% crystal violet. And then part 3. So basically that's a Beers Law plot that you're creating in part 2. In part, okay, so lock answer, all right. Part 3, now that we know that the solution adheres to Beers Law, and we know the relationship between concentration and light absorbance, we can look at concentration over time. So then you're going to watch more videos, okay? And you're going to take more measurements over a period of time. And then you're going to graph it. Okay, so this is very much like what we did in class today, right? So if we want to look at concentration as a function of time, what will you do to linearize your data, right? Does concentration change linearly with time? Do you have to take the natural logarithm and plot it as a function of time? Or do you have to take 1 over the concentration as a function of time? What does it take to linearize your data? And then how do you determine order based on that? Okay, so it says collect data, make a graph, consider the rate laws, all right, and you make all of those graphs using putting the formula into this column, last column, and graphing it. And then you'll be able to answer the question, 0 order, 1st order, or 2nd order. And that's it, okay? So it's getting to know how to use the tool, collecting the data, making a Beer's Law plot, and making predictions from the Beer's Law plot, and then collecting concentration data over a period of time and using that data to determine the order of the reaction with respect to crystal violet. So I hope that gets you started with the crystal violet lab. I know there was a lot of confusion about how to read the transmittance values. So you have to get used to those little ruler things and making distinctions between different shades of gray, literally.